Good morning, everybody. Happy to be here today. My name is Antonio Marques from King Juan Carlos University, Madrid, Spain. And on top of being the person who has been annoying you with emails for the last 3 months, okay, I will also be the moderator of our last panel, okay? Before I start, I should say that I'm very happy to be here, okay, back in what I consider my second home. Good memories are everywhere, and seeing friends that I haven't seen, lab mates for so many years is great. So I think that Alejandro did a superb job, and I want to leave this part for the afternoon event. But yeah, that is just a sample of a picture. I think that more than half of the people are here. I think that this was in 2006. Okay, and just a small sentimental part, one of us, Eric, over there, unfortunately passed away like 4 or 5 years ago. So it would have been great having him here as well. Okay, so coming back to my job for the next hour, okay, we will be discussing this last part of the workshop, networks and networking. Okay, we already discussed how important system engineering was in the signal processing view. Okay, we can view networks as a type or particular type of system, and indeed that is one of the things that I want to the panel to discuss, the multiple meanings that networks have, okay, and which are more suitable for people with our background. So the structure will be very similar to the other panels. We will have some questions. One of the panelists will address the question, okay? And then the other panelists, and of course you, the audience, please can add on that, even disagree with some of the things, and then we will have a richer discussion. Just a very brief introduction with no particular order. One of our panelists is Hao Su, okay, that she is now an associate professor at the UT Austin, okay. She was one of my lab mates here, so it's great having her here. So she works on learning and optimization for future energy systems. I don't know how she handles, but okay, she has 2 kids, and on top of that, she's an editor of 3 different journals that also I think that represent very well the richness of networks. And she used to be in Urbana, now she's at UT Austin. And I have to add that I've seen you in some Fox News interviews after you moved to Texas, so I don't know if that is related to that fact or not. But yes. So another of our panelists is Antonio Ortega, that is a professor also of electrical and computer engineering at USC, who used to work or still works in image and video processing, but in the last years he also has been one of the main leaders in signal processing over graphs, and that will be one of the themes that we will discuss, how different are graphs and networks. Are graphs a good model for networks, and also has a number of awards and service to the IEEE. And our last panelist is George Karypis, okay? So I think that it's good to have the dual view, in this case, of computer science, okay? He's a professor here at the University of Minnesota, but also is a senior scientist at Amazon, AWS. So I think that is also very, very important to have that view. And again, if you see his activity, I don't know how he also manages to be like involved in so many conferences and so many things. Very good. So let's start a bit. So I would like to start with some historical perspective, and basically how have you observed the evolution of the role of networks and graphs, okay, in signal processing and machine learning over the last 3 decades, we'll say, and related to this, a second question that you can address both or separately. What do you think that is the current, not the past, but the current significance of networks and graphs in our area? So, Antonio.
All right, thank you very much. It's a pleasure to be here, and I'm also here representing Yorgo's first academic home in the US, one where he's come back frequently, and we've developed a habit of throwing parties for various reasons, anniversaries of the Signal and Image Processing Institute. It's always a pleasure to have him back, and I've gotten a lot of excellent advice and input from him over the years. Not only that, but as I started working on graph signal processing, I've also interacted not only with him, but with his extended academic family, including, children, Antonio, Yanin, of course, Alejandro, Gonzalo, but also grandchildren like Santiago and others. So there's a very wide family working on lots of topics, and I'm really honored to be here, and congratulations. So thinking about the historical perspective, I thought I would say several things, about history, but the first thing I want to say is that, if you think about signal processing, you think about processing signals with a definition of frequency, right? So the spectral component of signal processing is fundamental. And I'm going to talk a little bit about the historical perspective on, in particular, graphs. And I think there's a question about when should we talk about graphs and when should we talk about networks. I'm going to hold off on that. I'll talk about graphs for now. So more on the mathematical side and the model side. And so the first thing I want to point out is that if you look at two workhorses of signal processing, the discrete Fourier transform and the discrete cosine transform, they both have graph representations. And these transformations have been used without the graph interpretation and before the graph interpretation became clear, right? So for the DFT, we're looking at thinking of finite length discrete signals in terms of a cycle graph, right? With a cycle graph, we get circular matrices. The circular matrices are diagonalized by the DFT. Lots of good things come out of that. The DCT used in basically every phone, every camera, every video encoder, decoder, can be interpreted as the eigenvectors of a path graph. Again, that connection appeared, a bit later. And in both of those cases, we have a time-space interpretation and a frequency interpretation. And these are things that have been around for a very long time. Now, looking at things that have happened more recently, I think that we've seen over the course of these days multiple applications of communication networks, computer networks, distributed systems, right? And many of these systems are smart grid. Actually, throughout these few days, we've seen examples, and so these systems can be addressed from a purely spatial perspective, or you can introduce some spectral components. I'm thinking about Ali's presentation yesterday, where he talked about Perron-Frobenius theorem and the spectrum of the distributed network. And I think historically we've seen multiple applications where people have first thought about the problem from a space perspective, then have introduced some spectral information, and I see graph signal processing as taking that one step further and using a full spectral representation. A couple of examples of that in image processing. So my colleague Richard Leahy at USC proposed a segmentation technique that was based on cutting the graph, representing the pixels connections as edges on a graph and finding cuts. And initially had an algorithm that just considered the graph itself. Then there was a very influential paper by Shi and Malik at Berkeley that proposed using the spectrum of that graph to find the optimal cut, normalized cuts, right? So this is part of this step of first considering a graph model, then seeing how the spectrum can help beyond, just not considering only the spatial information. Another example, sensor networks. That's how I got into graphs and graph signal processing. You can think of algorithms for consensus, for local interactions, and then you can look at the work that Ali presented, and you can do a lot more by considering global information spectrum. How I got involved personally was there were papers that were looking at doing transforms over sensor networks, right? So defining a frequency representation for those kinds of signals. And that led to wavelets on sensor networks. And that's basically how I got involved. I think what we see now, if I go back to Alejandro's presentation, he made the analogy between CNNs and graph convolutional networks. So that's one example where you say you can do CNNs for images. You define standard filters. They have a frequency representation. Now you make the analogy with graphs. Graphs have a frequency representation, and then you define spectral filters for the graphs, and you learn those. And so, again, sort of wrapping up, and others will probably have to add to this. I would say in this evolution, I see examples of systems that can be represented as graphs, and then we develop some spectral information, maybe the lowest frequency eigenvector that is very useful. And then what we're seeing now is using the full spectrum, all the eigenvectors and all the eigenvalues. Maybe the last thing I would say is that the analogy is great. So we have all the toolbox in signal processing that we can use for graphs, but the analogy has lots of limitations. Graphs are irregular. Directed graphs are very difficult to work with. And I don't think we should think about graph signal processing as working with a single graph, but working with different graphs that are different depending on the application and developing tools that are specific of those applications. And one example of how different graphs are, we're used in signal processing to think about time frequency trade-offs, right? You can get exact localization in time, but if you do that, you don't have good localization in frequency, and vice versa. That goes out the window with graphs. And so you can have frequencies, eigenvectors of the Laplacian or the adjacency that are exactly localized in space and are pure frequencies, right? So I think the analogies are great, but as you go into specific applications, you have to be aware of the limitations of those analogies and understand that it all depends on the type of graphs that you're considering.
Okay, thank you. So any additional thoughts from the panelists or in the audience about the evolution of the role of networks and graphs in the last 30 years and the relevance for the signal processing and the machine learning community? I have to say, at least from my point of view, that I remember that one of the reading groups that we organized here, 15 years ago, or more in social networks, that concepts as the Laplacian matrix associated with a graph or things like that, were not known by the standard person in signal processing. And I think that nowadays, for example, they clearly are, right? So there has been a change there. Okay, so let me now also with a bit the historical perspective. So which type of networks you believe that the impact of signal processing and machine learning has been more important, right? And to be more specific, yesterday, clearly we were saying that wireless communications was one field where signal processing has played a tremendous role, okay? But maybe, or this is debatable, it's unclear if the networked part of it or the distributed part of it was really important or not, right? So do you think that wireless networks have been the most important, or maybe smart grids or even other types of networks? So how, I think that you have worked both in communication networks and now in smart grids. So how do you see that?
Yeah, I'm really glad to be back. Thank you for inviting me. And I think I'm here with a lot of lab mates. We started in 2005, 2006, and really glad to be back to our academic home in Minnesota. So I would like to comment on the question specifically on the type of network that I work mostly on, which is nowadays in the electric power systems. So I think when we work on the problem, one of the first problems we tackle were like a monitoring aspects. So whenever you have a network that you have information acquisition and information fusion, and then you want to infer the underlying system system, and that's a perfect the problem we work on with Yorgos on state transmission is a perfect example of that. And I think there were a long line of work on information fusion, where basically each datum is just a partial observation of the underlying system, and then you have seen the talks today, like on partial observation in graphs for topology identification, and also for graph learning earlier on. So I think a lot of problems are falling into this kind of instance, and this is one aspect that signal processing, specifically statistical signal processing, can play an important role on. So the problem we work on in power system on state emission, actually one of the first person who pioneered that was Schwabi, and he was working on radar signal processing, and he applied this idea to the power system. And I think in the recent years, when all of us working on smart grid, there is also a lot of these applications of great ideas from a statistical point of view and from a signal processing point of view into these real world networks like electric power grid.
Okay. So, any other thoughts about which type of networks the contribution has been more significant?
And I mean, I would go back to what you said about the language, right? That we, at some point when some of us first saw these kinds of formulations, said, well, this is general. It's a way of representing data, connections between points, and then I think it's. I would say that the biggest contribution for me has been having another tool, another way of understanding, formulating problems, right? And then where you apply those. I personally have gone back to things that I was doing in my PhD and right after that in image compression, video coding, and I found different ways of, defining twisted DCT that I mentioned earlier. So in a way, it depends what topics you're interested in. It's a new tool set, new ways of thinking, new ways of formulating.
See. Any other thoughts? Okay, no. So if not, let's move to something that we already discussed, that is this variety of networks that we have, that we use the same word for things that are indeed very different. And I think that the talks that we had, not only today, but yesterday, are a perfect example of that. We had one on smart grid, another one on wireless networking. So even the plenary of yesterday, or Alejandro by Ali, or Alejandro's talk today, that is more on distributed control and adaptation and learning, or just using graphs as some structure for data and to use that and to learn or to perform learning or estimation and prediction better, right? And to all those things, we use the word network, but indeed they are very different, right? In some of them, we have flow conservation constraints that are critical, most likely in power networks. In other cases, we are just exchanging information, right? And that those dynamics are different. So my question is how do you see this? Is this an asset? Is this a problem? And once again, so which are maybe the ones that are more suitable for people with our background to attack, right? And by our background, I mean, again, not only signal processing, but signal processing, machine learning, AI. So George, as a representative of that, please address this.
Okay, first of all, I feel like I'm the outlier here, so at least I'm one of the few outliers. And so Yusuf is over there, so at least there's some, we have someone else from a computer science background over here. So first of all, thank you for the invitation. So I think it's a great event. And unfortunately, I could not attend the first 2 days because I was out of town, but I did manage to get here just for that. Okay, so the question is about networks and graphs and the whole spectrum, right, in terms of, signal processing approaches versus more traditional graph machine learning approaches and so forth. So I'm not a signal processing person, right? I'm more of a graph machine learning person. The type of graphs and networks that I usually deal with, they're either small graphs, the type of graphs that comes in from modeling small molecules or proteins, right? Or they're the type of graph that come out from like social networks, information networks, and knowledge representations in the form of a knowledge graph, and things of this type, right? So I think those are which by nature a lot of the data is heterogeneous, right? There's some information on the edges, but there's actually a lot of information on the nodes, right? And the edges tend to be actually, in many cases, very much information rich, right? And very different in nature, right? So that gives rise to a whole different set of problems and methods, right, that you like to tackle on that. Right. So in terms of now, but what was the crux of the question? So that's the problem with his questions. His question is like a paragraph long, right?
Whether that diversity that we have, is that an asset? Is that a problem? Is that an opportunity?
I think diversity is always an asset. And the reason for that is for many ways. So number one is make sure that whatever we develop, right, it can generalize across a different set of problems, right? So number one. Number two, different types of graphs will require different types of approaches, right, and entirely different set of thinking in terms of how you tackle them, right? So this is one of those things, one method, right? So there's no such a thing as the big hammer that will work on all the different graphs, right? And we need to develop a specialized method for those. I think, the opportunity that I see in that variety is that, ideas are coming in from signal processing and, operating on networks that I would call them simple networks. I mean, you guys can be upset with me for that. But, they're kind of, homogeneous networks in which, the nodes are the same type. The edge, it's the same single type of edge and you know what it is, right? Taking those things and applying them on graphs that they are significantly much more complex, right? And I think leveraging at least some of those ideas and generalizing them, right, is an asset in that community. So now in terms of methods, and I think there was a question or something like that. I think the methods that we use for small graphs are fundamentally different from the method that we use for large graphs, right? And one of the key fundamental difference in a small graph, I can actually operate on the entire graph, right? As opposed on a network, right? In one way or the other, I will kind of, pay attention to some of that information that they're much more local, right, than the other information in the network, right? So that gives rise to an entire set of methods and approaches to tackle those things.
How do you want to add something on that?
Yeah, I think I agree with that. This diversity could be an opportunity. So in the real world networks that we work on, so there is a physical network, as what you're saying from the flow perspective. There's also what we call the inference network that, maybe one location is using a lot of power, but then it can increase the price in a lot of other locations. So it's not necessarily bounding by the physical connectivity per se. So, but then the complex interaction between that could be some opportunities to look into. Yeah.
Right. So indeed, while the microphone arrives, is like the approach that someone, for example, in network science or what they understand as a network and the tools that they use is very different from the approach that we use, right? So.
Thank you. I just had the privilege of having an office next to George. He comes from northern Greece. I grew up in southern Greece. If you want a joke, they call us, Africans. We call them Bulgarians. So, a number of weekends we walk around or ride on a bike with George. And if you want, you can comment on one thing that we touched upon last time. And I think this community, SP, is well trained to contribute. That is that of dynamical systems. And you want to talk a little bit about opportunities in diffusion models or what those are? That could be, I think, something useful to pick up your brains on. So what do you think about dynamics in dynamically evolving networks?
This is actually a very, very good topic. I was talking to somebody that, actually I was talking to one of my students that I haven't had a chance to give him comments for his newspaper yet, because I was working on an AI Institute proposal that was due yesterday. We have, I mean, in many settings, we have, very much dynamics, right? So, and there's a lot of processes like diffusions on graphs or graph-like of data, right? So in that particular context, we're looking about diffusion in the context of material science for generative models, right? In which, you can have a graph-based representation of the composition and, how do you diffuse a thing to get a generated structure, right? And there's similar type of, diffusion of a graph kind of models in a generative context for protein structure, prediction generation. But network dynamics, they're all over the place, right? So we have, we don't have cameras, right? Okay. So nothing is being recorded, so to speak. So networks, as you know, you guys was mentioned, I've been at AWS for about 5 years now. I'm actually coming up on my 5-year mark, beginning of June. And within AWS and Amazon at large, they're very large networks, right? And we have networks both on the physical infrastructure side, right? And being able to model the networks, within AWS. We have a lot of networks that arise from modeling information flow and things related to interconnection networks, on the data centers, as well as fraud and abuse related networks that arise both within AWS as well as Amazon at large, right? I mean, one of the most important applications of graph machine learning in Amazon, and I think Vasilis is somewhere here in the room, is around actually fraud and abuse. Right. So, and of course, the second most important application is about recommender system that was mentioned over here, right? So that's the usual suspects, right? But all of those things have a lot of dynamics, right? So, and things evolve over time, right? So being able to model those things is actually very important. And I don't think right now within the traditional machine learning community, we have the right set of tools to model those dynamics, right? At least, from my side of the fence, so to speak. Right, the type of method that we have, usually are very computationally expensive, and it's very hard to scale them to extremely large graphs. Right, so anything that will allow us to model those dynamics, I think, would be very useful. Right, but again, those are networks that are very, very different in nature, right? To a lot of the networks that I've seen people in signal processing community working with, right? It's the complexity and the heterogeneity of the network is part of both the business impact, the business value, as I was, one of the features and the bugs, so to speak, right, of the system, right? And being able to handle those things is going to be very important.
Good. So let's move to the next question. That is the last one about these multiple minutes of networks and the relation with graphs. As we said, I think that we all agree that networks are something more general, okay, and that graphs are mathematical objects that are very well defined. But it's also true that in most approaches for networking, we use the graph, right? And the graph has this limitation and very clear definition, right? There is a set of homogeneous entities that are the nodes, and there is some kind of relationship that is given by the edge, right? So my point there is, do you think that this has somehow limited the approaches or the tools that we have designed for dealing with networks?
Your definition for graph is different than my definition for graph. So, I already mentioned, at least in my view, one key difference between networks and graphs, at least in my mental model, right? So networks are much larger in general than graphs, right? But this is more of an operational difference. So first of all, I don't consider graphs to be homogeneous, right? In my view, graphs are, it's a set of entities and a set of relations, between entities. Those relations don't have to be involved just a pair of entities. It can involve, multiple entities, right? So we're talking about hypergraphs and things of this type. They're not, the nodes are, have very complex features associated with them that make them, by definition, very different from each other. The relations are the same thing, right? So when I think of a graph, and a lot of the real-world graphs that arise in a lot of business applications, or well, science applications, right, have these type of characteristics, right? So and the machine learning method that we're developing for learning on graphs need to be able to handle those things, right? So.
Yeah, so I think you can make the differentiation between the two in different ways, and maybe it doesn't matter. So there will be. So my first thought would be that for me a network is related to some application. Maybe that's a physical application. There's something that exists that is. A road network, smart grid. So there's something physical. And graphs are representations for information that can, in turn, be related to something physical. Like, for example, for images, if you do image segmentation, pixels become nodes. You have a graph that connects pixels, right? So I tend to think of graph as something we use to model, whether it's only graphs or hypergraphs or some other object, and whether it's the graph exists or we created it to represent the connections between information. Maybe it's a different question, right? But I tend to think network something physical, graph is more of a model, or a model to represent information. I would say, not just a mathematical representation, but how we think about relations between there could be different mathematical models for specific graph, like recommendation networks, or but maybe it doesn't matter. That's fine.
Yeah, I don't want to get into the fight on the terminology, but I just want to point out that, indeed, I agree that the distinguished future you mentioned, that one is like whether there's a physical connection or there's some kind of relation between the nodes that could be different. Actually, in Steven's very nice talk, you introduced us to the concept of virtual network, meaning that we actually may not know the physical line, the electricity line that connecting the nodes, but then as long as we know how the physical quantity, voltage, currents are related to each other. So I definitely in real world network there, like power grid, there are tens of thousands of nodes, but even on each node there is this distribution system that's sitting on it. So that's why we do Cron reduction. We do these techniques to extract the underlying relation among the nodes. So I think this kind of also related to the network of network, I think you mentioned. So I think there is a great opportunity for maybe signal processing optimization to look into this large-scale system. How can we extract them more effectively at the right level of resolution or granularity for the right problem of interest? So we do a lot of adaptive signal processing or designing algorithms that can adapt to different kind of granularity, different resolution in signal processing. I think this idea, this concept, it could be very helpful in like these very large scale networks or graphs that we're dealing with.
Just to add something there, in both your interventions, how you mentioned this idea of using different graphs for a network, right? And I totally agree with that. So, and I think that that is one of the problems. There is no a single graph. There are multiple graphs, right? People in neuroscience, for example, it's very clear to them. They have the structural graph when they want to understand the brain, and they have the functional, the so-called functional graph. And you said that for power grids, or we have a physical graph, right? But then we have also some inference graph that relates the state of the nodes, right? So I think that that is one of the main things. We need multiple graphs to represent this complex system that is a network, right? Okay, yeah, sure. Any question? Yeah.
Okay, so I have a few comments and mostly questions. I'm just trying to get a grip here. And okay, so somebody distinguishes between a real physical network and a graph as a representation. Well, you know, that's what goes on all the time in science and signal processing. We think there's an ontology out there. There's something real out there, and we pose some epistemological model for it. So this distinction between a network and a graph doesn't make any sense to me, because in science there's always this idea of something ontological and something epistemological. Okay, that's my first comment. My next comment is that I listen to everything here and I say, well, to me this sounds like multi-channel signal processing. Each node is a channel. And everything we do here is multi-channel signal processing. Is it okay? So yeah, could be heterogeneous. Okay, so where I'm getting to this is that let's say I know how to do multi-channel signal processing. So I have no interest in graphs unless, and I think this is the key point, there's something in the theory and methodology of graph theory that's going to bring new ideas to my multi-channel signal processing. I think I've heard Ms. Zhu say that there looks like there's something from multi-channel signal processing that might help us do graph theory, but I'd like to know what there is in the reasoning and in the mathematical methods of graph theory that's going to make me better at multi-channel signal processing. That was long-winded. I apologize, but I've heard you be long-winded before too.
No, I'm happy. I think you raised the point, and the panelists should answer first, not me. Yep. You go ahead. No.
I'll go ahead. So I don't think we ever defined what is graph machine learning, right? So what was the definition of graph machine learning here the last couple of days? No?
We understand.
No.
It's for you to define.
No, the reason I'm asking that is the following, right? So I don't think we're talking about a graph theory so far, per se, right? So what we're talking about is learning on graphs, right? And when we say about learning on graphs, right? So at least in my view of graph machine learning is I want to solve a particular problem, right? So a particular problem, let's say I want to compute a representation of a node, right? That I'm going to use it for some sort of a downstream task. Right, so it's like a classification, a regression, or even a link prediction task. Right. So when I think of a graph machine learning, is I have the node, right, as kind of I can use all the information associated with the node to solve my problem. Right. Now I can impose some sort of a graph information, right, or at least some sort of a graph prior, right, that will tell me that, well, it's not enough to use that information from that node, but we can potentially take advantage from information from other things beyond that node, right? And that which is perfectly fine, right? So which is so and then the whole idea is, again, you can have a very, very crude analogy, right? So for essentially getting a representation of that node is that if I'm going to do some sort of a data augmentation, right? So by leveraging information from the rest of the nodes, right? Or I'm going to use a representation of that node, right? That is somehow gets influenced, right, by the rest of the stuff, right? This is to a large extent what graph machine learning is. Right. So, and it's now And that goes back to the signal processing community. That's why I'm actually, struggle sometimes, is because I think signal processing is a very antiquated term. I think, to a large extent, this is machine learning, right? And statistical machine learning. And I don't know why signal processing has been kept as a name around. And again, that goes back to the core, the whole idea of different communities, right? Using terms that do not, essentially mean the same thing and not necessarily communicate, right? So there is a question of semantics and sharing vocabulary right across the community.
So I come from the same process, machine learning background, and so I should have something to offer.
So let me try to help. I don't know if something to you, but let me try to address the multi-channel question. I don't know enough about multi-channel signal processing to tell you if I have something to offer, but I think of graphs, or graph representation. So if you want to think about the information at each node as a channel, right? And then these are systems that allow you to consider millions of channels with completely arbitrary relationships between the channels, completely irregular. They cannot be described, they could be described by an embedding in a high-dimensional space. They could be directed or undirected. And if you represent those relationships between the channels with, let's say, a graph Laplacian, you can approximate those relationships locally, right? So you can do some local processing instead of processing across a million nodes. You can also have a spectrum that corresponds to the observations in each of those channels and how they relate to each other, right? So you have a frequency representation for the relationship between the observations across the channels. Does that answer your question?
Multi-channel machine learning, yeah.
Let's yeah.
The simple answer is that what you call multi-channel signal processing would be a fully connected graph. But this is a sparse multi-channel signal processing. As you said, you can have local information amongst a few channels that, you do local processing and all that. So I think that to me is a distinction.
Yeah, with due respect, I'm talking about multi-channel machine.
Michael, yeah, Steven has a...
So I have a comment, maybe it's related to what you said, what graph structure or methods can help with signal processing. Except I don't know too much about signal processing, but I'll give you an example in controlled dynamical system, which perhaps is related a little bit to Yorgo's earlier comment, given aspect of dynamics on graph. So even if you think about a LTI system, x star equals ax plus bu, there's an underlying graph in that model. So it turns out that if you look at questions such as controllability, then graph structure actually plays a role in the controllability or stability condition for your model. So it's not signal processing, but it is, say, controlled dynamical system where graph concepts, graph methods actually plays a very important role. And one concrete example of that is if you have a graph, which is actually a power network, if you have a graph, there's certain dynamics. So this is the fast timescale behavior where you do have dynamics. It's not the phasor that I talked about, where you describe your behavior by ODEs. Then you ask, you have certain dynamics on that graph. Then you say, okay, if I can control only a subset of the nodes, So I can put controller at subset of nodes. Which nodes do you place your controller so that the this dynamical system defined by frequency controls and on power networks and so on is actually controllable in the normal sense of controllability. Or it turns out that you have to look at the Laplacian and the eigenvectors of Laplacian gives you some kind of a coverage concept that determines exactly where you need to put the controllers so that your system is actually controllable. So I guess this is one example where the structure of the graph, the method of graph actually plays a very important role in a different domain. So I hope that there's a similar thing for signal processing, but I don't know too much about signal processing to know.
So I actually think that is a very interesting discussion and can lead us to the next question. If we focus now on the use of graphs for data, machine learning, signal processing, okay? So I think the discussion is what does make graphs appealing in this context, right? Is it their model accuracy? Is it the fact of being interpretable? Is it the fact that maybe can address also some part of Luis' question, right? That because of being sparse matrices, some of the computations may be easier to implement. Or is there mathematical tractability? Why are graphs relevant then or convenient to represent data?
I'll start. By the way, sparse graphs are really bad to compute on. Dense matrices are always much better from a computational standpoint, right? But that part aside, right? So I think graphs are very important in the domains that we don't have an infinite amount of data. Right, and the reason for that is because they provide relevant priors in a bunch of different applications, right? And this is I think there was a discussion earlier about transformers versus attention versus GNNs and so forth, right? So in many domains, what we're finding, and again, this is an empirical finding, right? If we have a lot of data, we can just get away with just attention. Right. So, and sure, there are some sparse priors, right, in terms of how information, what are the dependencies among the data, right? But that kind of dependency is discovered on the fly, right, as part of the training process, as long as you have a lot of data, right? But that only works if you have a lot of data. Right? If you don't have a lot of data, infusing some sort of a sparse prior, right, some sort of a graph prior that you have on your data that you may have from that domain is very important. Right, so those are the areas in which I see the graph machine learning or some sort of a network prior is very useful.
Yeah, maybe I would add to that there's some applications where it's a natural model because the data is irregular in some respect. It's irregular in space, for example. So if, how I got started in this topic is through sensor networks, and sensors are wherever they are, right? That you don't get to place them on a regular grid to do Fourier transforms on them. And so how do you deal with irregular data, and how do you have methods to define frequency for irregular data, knowing that the points that you observe are likely to be correlated, the correlation depends on the distance. And so this provides, an extension of methods that have been developed in geostatistics, things like kriging, so to do smoothing interpolation for irregular data. And it's not just sensors, also 3D point clouds. There are multiple examples where the data is irregular. One other example of that is when you look at a data set in a machine learning task, you can typically embed the data in some space, and then you have examples that you use for training. And those examples, again, are irregular, right? So how do you do smoothing processing of data that is irregular in some Euclidean space? That's one of the things that graph signal processing can allow you to do.
Okay, so
Marques, thank you. Just to comment on the point that you made, I think it's an important point, and it's not far from the truth. So if you take a graph, or if you take a network, and if you write down a description for it, a state space model for it that tells you how the data is evolving over the graph, you get exactly what you're talking about. Okay? So if you look at the graph from a global perspective, what you are saying is correct. But the question in graph signal processing or processing over networks or graphs is the inverse problem. Meaning, what kind of algorithm, for example, if I give you a full-blown state space model and I tell you, given measurements, recover the state. We know how to do it. Once you have a full state space model, you can use a Kalman filter, a particle filter, right? We know how to do it. But if I tell you, you cannot solve it globally, you have to solve it locally over a sparse graph. Okay. So you don't have the global information, you only have access to the localized models. How do you solve the problem now? So when we talk about graph signal processing or processing over networks, you are focusing more on how do you extract information, assuming that you don't know this global representation that you're talking about. You only have access to local information, which is the local connectivity around every node. So that's one way to try to explain it. I personally distinguish between graphs and networks in the following way. And I have two ways to explain it. One of them, for those of you, for example, are familiar with the classical digital filter. We used to learn how to design a low-pass filter, and you end up with a transfer function, right? A transfer function, that's a constant transfer function. You implement it, and then it performs, it's filtering. And then you move from a static digital filter to an adaptive filter. So what's an adaptive filter? It has dynamics inside it. That filter, you cannot describe it by a transfer function, for example. It's always evolving. It's always dynamic. So this is the difference that I make between graphs and networks. Networks have a life of their own. So if you remember yesterday when I referred to the algorithms we were talking about, I referred to them as adaptive networks because they have these dynamics. They're always learning. They're always changing. Right? Of course, there are many other ways to describe these things, but these are some of the comments, that...
Okay, well, nobody needs state space diagrams, nobody needs rational models. That's besides the point. And when I talked about multi-channel signal processing or machine learning or time series analysis, I never said anything about spatial or temporal stationarity. So we can certainly talk about multi-channel machine learning for things that are non-stationary in space and time. So I still don't.
No, my question to you is this, right? My question is this. You have a multi-channel model, right? You need to have some model because you need to process the data to get information out of it. So implicitly, you are assuming you have some model, right? So how are you going to process the data? What kind of processing are you going to do on the data? Right, so this is you see, if you talk about a multi-channel model, which is a valid assumption, implicitly, at least from my understanding, assumes that you have access to all the data and you can process it. In these types of processing, the data is only localized. You cannot group it together and perform a full-blown multi-channel processing over it.
I just think that it depends on how broad you make your multi-channel processing. But I agree. You can say, I include temporal dependencies, nonlinear dependencies, spatial dependencies. But I also happen, we don't agree too often, but in this case I agree with George.
Do not agree that often, it's interesting.
The easiest way to think about it is that the graph provides a prior information. Take the simplest possible underdetermined system of linear equations. And this is exactly, you have a graph with 1,000 nodes, but you can measure only 50. Can you figure out the rest 950? No, because it's underdetermined, right? However, if you place a Tikhonov regularizer, or in this particular case, you can have your graph, and I guess the adjacency matrix times its transpose will give you a kernel matrix. That kernel matrix is nothing but, if you like to interpret it with a multi-channel viewpoint, it is like a priori knowledge of the covariance. Yes, but here the graph itself depicts nicely this information that this variable, that with that variable, they are connected. So that is the difference. I don't think, unless you specify the multi-channel signal processing problem you're talking about, they cannot address. But I just brought an example myself. But indeed, some of the easiest way is to think of network in an inference setting as a prior information. And if you like to call it Tikhonov, or you want to call it Bayesian prior with a Gaussian prior, which is like a covariance, weighted covariance, it's up to you. I think the question is how broad is your process.
Okay. So in the interest of time, unless you want to add, okay, over. You have 1 minute to close the discussion.
I want to address Ali.
Okay.
So
you can choose. You can choose which one.
Ali, in multi-channel machine learning, we don't assume that we have access to all the channels. In fact, a very typical problem is that we have a multi-channel problem, and we're going to use a subset of those channels to predict what's going on in the set of channels that we don't measure. So we have these, what we call virtual two-channel problems. Some of them are the measurement channels. Some of the channels will be predicted. So I guess I cannot accept your idea that when I talk about multi-channel signal processing, I'm assuming that I have measurements at every channel. Well, you need to know something. You need to learn something. But again,
right. Then you are going to
30-second rebuttal, and that's it.
But you are going to do your process certainly, right? Exactly. So, but here we know how to do it, right? Here we tell every agent you can only interact with your immediate neighbors to get to that information. Exactly. That's exactly what we are saying. You can do.
Okay. So let's move to a. I lost control.
15 seconds. So I know a little bit of multi-channel signal processing, a little bit about graph signal processing. I agree with what Ali said, but at the end of the day, I think Louis is right. It's multi-channel signal processing. It's also only.
We may finish this panel with a vote at the end to see. Okay, so let's move quickly to maybe easier questions. So actually I think that in the last discussion was very clear that some people see the graph as a prior or some description of some irregular structure, okay? And that is true in many applications, or from financial networks or whatever, when we have this time series of prices that we want to analyze. But it's also true that in many other applications, George, for example, recommendation systems was one of the previous ones, that you have worked in molecule estimation, the graph itself is the data, right? So do we need different tools to these two different paradigms? The one where the graph itself is the data and our object of interest, and the one where the graph is some prior on the description of the structure, or we can use the same tools?
I think so far we've been using very similar set of tools, right? So I don't think necessarily we need to have different tools. I mean, there may be a customization, for some of those things in the different areas, right? But I think the tools that we have are pretty general purpose, can be applied to both regimes.
So I agree that the tools are very similar, right? What we are using now, I don't know if that is correct or not, but it is. Okay, another easy question that was, well, at least short and well-defined question that was addressed before. Should we go for higher order interactions, and should we start to use hypergraphs, simplicial complexes, and things like that, or the simplicity of the pairwise interactions is worth?
Yes, we should go to higher order interactions. My mental model of that is the following: is if I know that they're higher order interactions, why not take advantage of it, right? So why throw away information, right? When I'm modeling the problem, when I'm trying to solve the problem.
Good.
So.
I completely agree. I think Alejandro maybe is gone, but he's done a lot of interesting work. Also Santiago and you, and so definitely higher order interactions. Yes.
Good. Less conflictive and questions. So let's move to briefly to the last part of the panel, that is to discuss a bit the future. And because this is being recorded, then in 15 years or in 20 years, we will have you on the record, right, to see whether your predictions are correct or not. Okay. So if you have to choose like one area where you think, an application area, let's say for now, where machine learning or graph-based machine learning or graph-based signal processing is going to be really important in the next 10 years, that they will change or revolutionize things. So if you had to choose one or to predict one, which one do you think that it will be?
Yeah, so for me, I think there's opportunity to connect to this modular design concept in traditional network system like we have in power systems, which I mentioned, like you could have a hierarchical view of the network. So you do the network as a collection of smaller network, but then still think about the interaction among the smaller networks. So a lot of issues like the dynamic population, safety and risk among this interaction, I think it's naturally related to graph interview system. So I think that duality of system is a great way to think about it. Yeah.
So I'm going to avoid answering that question, but I'm going to give Professor Scharf some homework. And the homework is to tell us if hypergraph is also multi-channel signal processing. Good.
So, George, your take on...
So it's a great question. So I can be contrarian over here, or at least some controversy, right? Maybe 15 years from now, the deep neural networks will solve all the problems for us, so we don't have to worry about what we should be doing down the road, right? So that's one point of view, right? But I think one of the areas that, I think it's worthwhile to see how, a lot of the graph machine learning or signal processing techniques on graphs can apply is actually analyzing the large deep neural networks that right now we simply don't really know how they work. Right, so I think this is an area that may require very different set of tools, right? But this is something that I think is worthwhile exploring, and the reason for that is the current regime of training larger and larger models will not get us very far, right? So pretty soon we'll be power limited, right, in training those models, right? And we're quickly getting there. Right, from an AWS standpoint, right, is the rate at which we can train those models is limited by how quickly we can get big data centers with power, right? So, so being able to see how well, the signal processing on graph approaches, right, or graph machine learning approaches can be used to understand those deep neural networks, or to help us design better architectures. I think that's an important area.
Thanks. Any other thoughts? Yeah, go ahead. Yeah, Vasily. While Vasily gets the microphone, and for example, I'm amazed but what DeepMind is doing with molecules to design drugs, right, and things like that is like something that I couldn't believe that was so relevant.
Yeah. So actually, I'm in a unique point where I spent like my last 10 years working with two jobs, with the tutor, actually, working my PhD with Professor Gianakis, and now just. So I think, in my opinion, one good way to view graphs is like that they connect like relevant information, right? And one like big challenge in today's LLM is, how can they deal with a huge chunk of information distributed out multiple files or multiple sources. And one way you can like solve that is through graphs. So I feel like one opportunity there is how can you bring the graphs to assist the large language model to summarize the information or the relevant information.
Thanks. Then in the afternoon event, we will ask you which George do you agree more? But okay, but that is for the afternoon. And let me just close with one last question for the panelists. Okay, so let's change a bit now. Not think about the application, but like a fresh PhD student or someone that just is starting his research career, and then that person is going to work on graphs, but is debating which problem to look at. So I want your suggestion in where to look. Is it like random models for graphs? Is it directed graphs and connections with causality, for example? Is it optimization over graphs? So which one will your advice will be, okay, I think that this is a cool problem. No, you have to answer the question. Yeah.
So the advice that I will give to students is do not work on graphs. But, right, if I have to give them an advice in terms of working on graphs, and again, here's my computer science bias is coming in. I think I will kind of focus not so much about the specific problem, right, but the applications, right, and that can be enabled by advancing graph machine learning, right. And I think anything healthcare and life science and medicine related, those are very important areas, right, in which any advances that we can make over there will have a significant impact, right. I will not tell the students to work on things that they have business impact, right? I mean, this is something they can work after they finish their PhD. But I think the areas that we look at things like biological networks, right? And you mentioned AlphaFold theory, right? I mean, it's amazing how quickly we can move in that space.
So I mean, I have students working on graphs, right? So I can tell you things that we're working on, but I'm not going to do that. I don't want to advertise my own work, but I think that I think applications are very important. And the one thing I always tell my students is that there's a lot behind every application, and if you want to explore an application where the group is not already working, that's a multi-year endeavor to just understand what the problems are and how things can be useful and what has been done and what are connections with things that have been done. So I'm always very excited about new applications, but I think it's a huge investment to jump into something new without collaborators and without some really study before you get to apply things. And I mean, there's never a hammer that will solve, things. I mean, it just never happens. You always have to go deep, understand the applications, and then maybe if you're lucky, there's some good solutions.
So since this is the last question, I would just say what Yorgos taught me when I was a grad student, what to work on. I think was mentioned earlier, work hard, play hard. That's definitely the characteristics, and work on the things that make you happy. Yeah. So I think, be passionate about what you do is the most important thing. When I was a grad student, I learned from Yorgos. Yeah.
So thanks. Any other idea? On my personal side, I will ask people like Mark or Petar, or I'm fascinated by random models for graphs. Okay, so we can have some tools to deal with uncertainty in graphs that untractable tools that can be then later used for inference problems or for whatever, I think that is a huge opportunity.
Quantum computing.
Good. Any other thoughts? So if not, let's thank our panelists again. I see Yorgos as an announcement.
One announcement. We can get quickly to the food, but because the photographer has to go, he prefers to take a group picture before we go for lunch. So if we can squeeze or move to one side and then use the steps to differentiate the height. Prefer outside? But there was a proposal for outside. That's it.
Yeah, we were thinking outside.
You prefer outside?
Yes.
Okay. Outside will be
outside the building. So
outside of the building.
Thank you.